Okay, folks. Any questions before we get started? Don't forget, your first exam I sent around an email today will take place, unless there's any objections. We'll start at 7:50 on Friday. Our review session Wednesday at 6 o'clock in Marketing 102. So we were talking about the homomorphism theorems, the isomorphism theorems. So this is the last thing that we talked about was the first isomorphism theorem. And this one is the nuclear weapon. So what it says is if you have a homomorphism, any homomorphism from the group G to the group H, then there's an isomorphism from G, this quotient group, G mod the kernel of phi, onto the image of wherever this went. And it is given this way, phi bar of this coset, that's what this is, G times kernel phi is a coset, is phi of G. We proved this last time, and the heavy lifting really was just showing that this thing in fact is a function, right? Because my input here is a coset. And so I might say tomato and you say tomato. G plus, my G times kernel phi might be somebody else's X kernel phi if they represent the same coset. We needed to show that this gives the same output, and indeed it did. After that, showing that this was actually a homomorphism was easier. Okay, any questions on that? All righty. There. The magnificently named second isomorphism theorem. And we will see as we develop these why the first isomorphism theorem is so cool. Here we have subgroups of G. But H and K inside of G be subgroups, and let's suppose that H is contained in the normalizer of K. So in particular, if K is normal in G, then this is always satisfied. If K is normal in G, then the normalizer in G of K is all of everything's normalized, and certainly H is contained in that. This might look familiar because we talked about this condition a little bit back when we were doing kind of the counting stuff. So our conclusion here is H intersect K is normal in H, and HK mod K is isomorphic Okay, so here's what the second isomorphism theorem says. It sort of compares quotients. If H and K are subgroups of G, and this technical condition H is contained in the normalizer, we'll see how this comes up. But in particular, this holds if K is normal. Then, does this look familiar? This is a homework problem, right? We already know that H intersect K must be normal in H, and HK mod K is isomorphic to H mod the intersection. Okay, so there's a lot to unpack here. The first thing is, do these things make sense? right? I'm talking about HK mod K like it's a group, right? And it is, but there must be something must be true for this to even make sense. Can somebody tell me what it is?
K and the intersection are not empty.
Okay, one thing to unpack is note HK is a subgroup. If this thing here isn't a group, this doesn't make any sense at all, right? Well, we know that HK is a subgroup of G because H is contained in the normalizer in G of K. In fact, that is a theorem that we proved earlier that, remember, one of the things we proved is HK is a subgroup if and only if HK equals KH. And we use that to show that a condition that's good enough is H is contained in the normalizer. So I know that this is a bona fide group, right? Otherwise, this doesn't make any sense at all. What else am I implicitly assuming here? Notice that this is a subgroup, but what else do we need? For us to even discuss this, I need the K to have what property as a subgroup of HK? Good. It has to be a normal subgroup, right? Certainly H is contained in HK because any K in here is of the form identity times said K. So this is certainly a subset, and we know it's a group, so it's a subgroup. We also need it to be normal. Why is it normal? Yeah. Yes.
Well, don't, if it's normal, then that mod or the quotient, it forms a group, right?
Mhm.
And for it to be isomorphic, they both need to be groups. So wouldn't K need to be normal then? Or that for?
Well, that's my point, right? That's
Okay.
right. I want to know why K is normal. Yes.
Oh, okay.
Can you prove it by saying everything in K must be in HK as H contains the identity? Therefore, everything in K is an element of HK. Therefore, products of those elements should also be in HK.
Well, that's right. That'll certainly show containment, but what about normality? All right. So let's check that. So let's check normality. So let K be in, well, let me call this one X. Let X be an element of K and let HK be an element of HK. Now I need to show that when I conjugate X by this thing, it's still in K. Agree? So let's check that out. Let's go HK inverse X HK. What might be the first thing that I do to kind of take this apart? Yeah, I agree with that. So let's do our inverse thinking. And I'll put some parentheses there. Everybody okay with me on that? Now, I'm going to make the wild claim here that this is in K. This little bit of parentheses here. Why?
Yeah, let me do it for assumption there that H is a subgroup of the normalizer.
That is right. What this means is anything in H normalizes K, right? So check this out. This is this is something in H conjugating as X and K, right? And this is in K since H is in the normalizer. Right? And so that now we've got it because this blob's in K and it's bookended by something in K. So this is in K. So therefore we get the normality. Are you okay with it? Yes.
Can you just repeat one more time about how then we know that that is in K?
You mean the middle bit in parentheses?
Yeah, the whole chunk and the middle bit.
Right. So remember what this is. This is all the crap in somewhere, G, such that Z inverse K, Z is in K for all K and K. That's what the normalizer is. And H is in there. So H is something in the normalizer. So when I conjugate this thing in K by something in H, it's still in K. Right? So now the thing in parentheses in there and the two bookends are in K. So the whole shebang's in K. Does that clear it up? So once again, that's where that, we've needed that assumption a couple of times, I think. Let me unpack the rest of it. This, we need that H intersect K as a normal subgroup of H, but that's part of the statement of the theorem, right? So, okay, so what have we done so far? I've convinced myself that this thing on top here is a group, that this is a normal subgroup of it. This needs to be a normal subgroup of that, but that's part of the statement of the theorem, right? So we'll move on to that in a moment. Yes.
Why again do we need it to be normal? The K.
Because this doesn't even make it sense. If this is just an ordinary subgroup,
Okay.
then this thing right here isn't a group at
And
all.
then we can have ice.
Right. Right, it's
Yeah.
not even, it's not even a
It's
group.
not a group. Okay.
Okay. So, continuing with the proof, we have shown in your homework that H intersect K is normal in H. Right? So that's the first thing that we need to show, and thank you, you all did it for me. So the last thing we need to do is show that isomorphism. And here I am going, so one might think, I'm going to write down some function from here to here and show it's an isomorphism. Or maybe a function from here to here and show it's an isomorphism, right? Can somebody tell me why I might not want to do that? What might be inconvenient about such an approach? Yes,
Maybe something to do with well-defined. That's
right. If you're going to have a function whose input is either one of these animals, these things on both sides of the isomorphism thing are both collections of cosets. So the first freaking thing you're going to have to do is say, oh my God, is this thing well defined? And you go through all this rigmarole. I am a lazy, lazy man. I would rather not do that. So I am going to do something else. We're going to define, I like to do as easy as possible if I can. I'm going to define a function that I hope is a homomorphism from H to this right here. Any ideas on what I might do here? I'm going to write this out rather. So my input is H, right? My output, it needs to barf out some coset, right? So it's blank K. Agree? What's the easiest coset representative? What's the easiest way I can make this map?
an H.
H. Now, of course, this thing has to be an element of HK, right? And so, and H is an element of HK, so I'll write this rather grammatically at first to give the idea, but after that I might suppress it. HE, emphasizing that the element H is actually H times the identity. This is something in H, something in K. Everybody okay with that? So I could really have just written H. Okay, so let's move this forward. Now notice, there is no question about well-definedness here. You give me an H, I give you the coset HK. No ambiguity, no well-defined, that's a function. Don't have to check any kind of well-definedness. If my domain had been this, I would have had to check well-defined. Yes.
So why did you choose that function to define it as?
This is a great question. Here is something you should always do in math. One of the things that make you all powerful is that you all are getting math sciences degrees or something like that. And math befuddles people. But let me tell you a big moral of the story in math. Always do the easiest thing possible, right? This is math. Make it easy if you can. And so I'm trying to go from here to here. And my strategy, if that's your question as well, my strategy is I'm going to use the first isomorphism there. Right? I'm going to apply this to the kernel. But the easiest way I can think to get from here to here, just from eyeballing this, is to do what I did. I know I've got to go to something times K, because this is a coset, and just I'm going to take this to the easiest input. Here's what I'm going to do, the strategy. I am going to prove that this is a homomorphism, that it's onto, and I'm going to find what the kernel is. And I'm going to apply the first isomorphism theorem. First thing, homomorphism. Of H1, H2. Now, how do I write these cosets out? Well, this is H1K, H2K, because that's the way we could break up cosets. And this is phi of H1, phi of H2. So phi is a homomorphism. Now, what may be a little bit less than clear is that this is onto, but it is. So I'm going to show that this is onto. What does a typical element of this look like?
Some H and H and some K.
Right, so okay, I claim first. I claim that these two cosets are the same coset. Notice that well, notice that H inverse HK, I think we could all agree with that, right? H inverse times HK is little k, which is in big K. Therefore, the coset HK equals H little k. So that claim is justified. Everybody okay with that? So notice H little k coset is equal to H k, which is phi of H. So phi is onto, because an arbitrary coset here is the image of H. Yes,
I don't understand how you connected those two.
this to this,
No, I understand that, the next part,
this.
yes.
This is from. Two cosets. Well, I'll call it K here just for convenience. This is one of our, this is our criteria for when two cosets are the same. These two are the same if and only if B inverse A is in K. And here you have B inverse times this is in K. Other questions? So what do we have about this? It's a homomorphism and it's onto. So let us find the kernel. Let me repeat my homomorphism here. Claim. I claim the kernel of phi is H inverse K. H inverse, H intersect K. Right. Let's prove this. Let's suppose first that X is in the kernel of phi. So phi of X, which is X K, right, is equal to the identity K. This means that E inverse X, which is X, is in K. Right? If this coset is K, that means that X lives in K, has to. And X is in H, because it's in the domain of this function, right? Remember, P goes from H to HK mod K. So anything in the kernel of phi is in H. Therefore, X is in H intersect K. So if you're in the kernel, you have to be in H intersect K. For the other containment, suppose Y is in H intersect K. Now look at phi of Y, which is YK. But this is equal to K. Because Y is in K. So Y is in the kernel of phi. So what we've shown is that the kernel of this homomorphism is exactly H intersect K. Now you all already proved this, but let me also point out as a parenthetical observation, H intersect K is the kernel of phi. That's what we just proved, right? Therefore, H intersect K is normal in H. Because the kernel of any homomorphism is a normal subgroup. So there, I kind of got that for free doing other stuff, right? You all proved this longhand, if you will, last time. But in this proof, we noticed that this is equal to the kernel of a homomorphism, so it's got to be a normal subgroup of the domain. By first isomorphism theorem, H mod kernel of phi is isomorphic to the image of phi. But here, the kernel of phi is H intersect K, and the image of phi, since it was onto, was the whole shebang. Okay, any questions on that? Yes.
A while ago, but how does inverse E X equals X mean X is in K?
Right, so these two are the same. I put that in there for emphasis here. XK is EK, right? And I use that criteria. This E inverse X is NK, right? Because remember, AK, these two cosets are the same if and only if B inverse A is NK. So that's the criteria I was using. Okay, other questions? Okay. So this next theorem is actually kind of another important piece here. And once again, we'll be using the first isomorphism theorem pretty heavily on this. This is another shocker, the third isomorphism theorem. Sometimes this one is called third isomorphism. Any questions before we hit this one up? Third isomorphism. Suppose N is a normal subgroup of G. And I'm gonna give you an application of this one before we jump into proof here. And there's a one-to-one correspondence between the normal subgroups of G containing N and the normal subgroups of G mod N. Correspondence between the normal subgroups, and I'll put this in parentheses. Oh yeah, sometimes this is called correspondence theorem. Between the normal subgroups of G mod N and the normal subgroups of G containing N. And what is more, yeah, it's more. And what is more is additionally, if you have an intermediate group and H is normal in G, So if you have an intermediate group between G and N, and H is also normal, then, H mod N is normal in G mod N. And G mod N mod H mod N is isomorphic to, anybody will take a guess at this? G mod N mod H mod N. What do you hope it is so you can remember easily from the symbols? Perfect. So this is sometimes called the correspondence theorem. Before we dive into the proof, let me give you this might sort of maybe help us get under the hood and figure out how this works. So my example will be following question. How many subgroups of Z are there? Containing okay, so take the ordinary integers, right? That's a group. Now take the integers that are a multiple of 12, right? That is a subgroup, right? It's just every freaking multiple of 12. It's a subgroup, right? My question is, how many subgroups of Z are there in between 12Z and the parent group Z?
Factors of 12.
What's that?
Factors of 12.
That's right. But this might not seem too trivial when you think about it, because really what you have here is this is an infinite group, right? It's an infinite set, and this is an infinite set. So it occurs to me that this could be a very large number. However, the third isomorphism theorem helps us to sort it out. It reduces this, how many things are there? You've got this infinite group, you've got this bigger infinite group, small infinite group, bigger infinite group. How many infinite groups are there between there? Seems kind of confusing. The third isomorphism theorem here helps us reduce this quite a bit. And I'll show you how. So we read this. Okay, this seems to be predicated on normal subgroups. Tell me why, in my example, the issue of normality is a non-issue. Anybody?
Alien?
It's a billion. So any subgroup that I happen to encounter would have to be normal, right? So I never have to worry about, is it normal, is it not normal in this particular example, right? It says there's a one-to-one correspondence between the normal subgroups. Oh, by the way, let me tell you how to read this. There's actually a one-to-one correspondence between the subgroups of Gn and the subgroups of G containing N. You can also add normal. There's a one-to-one correspondence between the normal subgroups and the normal subgroups as well. Anyway, in our case here, in our example, everything's normal. So here the role of G is Z, the role of N is 12Z. And it says there's a one-to-one correspondence between subgroups of G containing N, that's what I asked about, and the subgroups of G mod N. We've seen that these two groups are isomorphic. Z mod 12Z is a finite group, right? In fact, It's a really nice finite group. It's cyclic of order 12. So how many subgroups are there? How many subgroups are there of Z mod 12Z? That smells right. Let's see. And how can we tell? What's true about a cyclic group? You want to count the subgroups? A finite cyclic group, I should say.
Anything that has finite order.
There should be one for every divisor of the order, right? So let's see. Subgroups. One of each order, so one of each dividing, in this case, 12. 1, 12, 2, 6, 3, 4. I guess there's 6 of them. Oh. Right.
In this example,
Well, so that, what that means is, for the original one, right, the subgroups of Z that contain 12Z, there's one of each. How does this correspondence work? So the way this correspondence works is, let me just list it. The subgroup of order 1 is just 0 bar. The subgroup of order 2 is 0 bar, 6 bar. The subgroup of order 3 is 0 bar, 4 bar, 8 bar. Subgroup of order, oh, are you picking on me because I left out 6?
no,
Oh,
you
what?
have 6. Are these being pulled from Z or 12Z?
12, Z mod 12Z. These are the subgroups of
Shouldn't
this.
Shouldn't it not include 12? Because 12 isn't in Z mod 12Z.
12 is 0.
Okay.
Order 1, order 2, order 3, the subgroup of order 4. Subgroup of order 6. And the subgroup of order 12 is all of Z mod 12. What are the corresponding groups? Which one corresponds to 12Z? 12Z mod 12Z is just the identity. This one corresponds to 6Z, 4Z, 3Z, 2Z, and all of Z. This is the way the correspondence is going to work. So in fact, this is what we've discovered. There are only 6 groups that are contained in the integers that contain Z mod 12Z. All of these contain all the multiples of 12. And the correspondence works, take this one, take every one of these mod 12, and it will give you this. Z mod 12Z gives you Z mod 12, 2Z mod Z 12Z gives you group of order 6, 3Z mod 12Z gives you this, and so forth. And I think this is actually going to kind of give us the idea of how the proof is going to go as well. Okay, any questions? Okay, let's go through this and show the correspondence. Here's the way the correspondence works, by the way. if then H would go to, H mod n. So if I have a subgroup, of G that contains N, then the corresponding subgroup of G mod N, is H mod N. So let me make that a little bit more formal. Suppose I have an intermediate group H. Since N is normal in G, N is also normal in H. So H mod N is a group. Because N being normal in G means that it's also normal in the subgroup. And I am going to define F from the set of subgroups of G containing N to the set of subgroups of G mod N. And I'm going to define. So this is going to be my correspondence here. My input should be a subgroup of G containing N, like H here. And this is going to be defined this way. This is a subgroup of H mod N. Note, should make this remark at least. As H is a subgroup of G, H mod N is a subgroup of G mod N. Notice that certainly H mod N is a subset of G mod N, right? Because this is just the cosets where I take the representatives from H, and this is the bigger set where I can take it perhaps from all of G. So notice that if H1 and H2 are in H, then H1N, H2N inverse equals H1N, H2 inverse N, which is H1, H2 inverse N, which is actually in H mod N. Because H is a subgroup, so H1, H2 inverse is a representative, coset representative in H. So this correspondence does take a subgroup of G containing N to a subgroup of G mod N, as promised. Now I want to show that this correspondence is, well, I want to show it's one to one it on to. So on the other hand, I want to show that I cover every subgroup. Now suppose that we have A as a subgroup. G mod N is a subgroup. Suppose that you have just a subgroup in here. I want to show that this subgroup must be of the form H mod N. So it's not just some kind of random thing. Notice that A is a subset of G P mod n. There exists. So it's a bunch of coset representatives, right? So there exists a subset H of G such that subset such that H n is in A if and only if H is in H. So all I'm saying here is this A, this subgroup, must be some collection of it's got to be a collection of cosets. This group, right? And and so this forms some set, right? It's whatever the set of coset representatives are. And it's my burden actually to show that this set is in fact a group. And I will do so presently. So to this end, we show now H is a subgroup. So to this end, let X, Y be H. Let me also point out that, of course, everything in N is in A. So A is actually a subset that contains everything in N. Because everything in N makes this the trivial coset, which has to be in A. So let's take any pair X, Y that's in H, then X H Y inverse H is in A. Right, because this has to be the group. Therefore, X Y inverse H is in A. So X Y inverse is in H. So H is a subgroup of G that contains N. Right. So this means that H is a mod N, or I'm sorry, this A H mod N. And we can do the correspondence the other way. That is to say, if we define G of A, which is G of H mod N, equal H, then this gives a correspondence in the other direction. So EF and in the other direction, FG gives identity. Let me take you through one of it. So if I start with a subgroup of H that contains A and I do F to it, I get H mod N. And then when I do G to that, it takes it back to H. Right? If I start with H mod N, this correspondence gives me H, and then when I mod out, it goes back to H mod N. So when the correspondence in both directions gives the identity, that means that this correspondence is one-to-one and onto. So what do we get out of that? Well, we get that this gives our one-to-one correspondence. So what I've done is I've given a, so here's what we've shown so far. There's a one-to-one correspondence between subgroups of G mod N and subgroups of G containing N. The pieces I've got to fix is I'm going to convince you all next time that the normal adjective works when applied, and this last statement about quotienting out. But this is a good place to quit today. Any questions? Okay, I will see you for the polls.